So, hello everyone. I'd like to welcome you all to the technical session number 3. So, it's my pleasure to be the chair for today. Uh, we're going to start with the first talk for this afternoon. So, I have the word conservative sharpening filter for interpolated images. It's going to be presented by Leonardo. Please go ahead. Yeah, thank you.
Hello, everybody. My name is Leonardo. I am a professor at the Federal University of Rio Grande, and this presentation is about an evaluation of sharpening filters applied to magnified images. Image magnification is an improvement in the resolution of an image, which allows one to obtain a higher resolution image from a low resolution one. There are many types of magnification methods. They can be classified into reconstruction methods, learning-based methods, and interpolation methods. Next, we talk about some interpolation methods for image magnification. There are many types of interpolation methods for image magnification. On the simple polynomial methods, others which are a bit more complex. Most of the interpolation methods have in common that the methods generate a bit of blur as a byproduct. This issue should be relatively easy to solve. One could apply sharpening filters, which is our next topic. Also, as you can see, there are many options in the literature, which leaves us with a question. Why should we propose a sharpening filter specific for magnified images? Now we present this filter and try to answer this question. The best neighbor filter was recently proposed by us. It takes a low resolution image S and an image R, which results from the application of an interpolation algorithm applied to S. The filter mixes information from both the original image S and the interpolated image R, replacing each pixel in R by its so-called best neighbor, which comes from the original low-resolution image S. Best neighbor is a nearby pixel from the original image, which is the most similar to the corresponding interpolated pixel. The filtered image can be combined to the interpolated image by using this linear combination. Now we show the results. As you can see, on top of the bicubic algorithm, our filter achieved statistically significant improvements in the quality of the images for all magnification factors, for both SNR and structural similarity for both image sets. Now, considering other sharpening filters and on top of other interpolation methods for the Morgfile 25 set, as you can see, the LUM filter and BNF were both able to increase the average PSNR for this set, except for the INDI algorithm, where only the BNF filter was able to achieve statistically significant improvements. Now, for the same image set and the same interpolation algorithms, you can see that the LUM filter was only able to achieve significant improvements for the images from ICBI, not from the other interpolation algorithms. BNF was able to improve the image from all the interpolation algorithms used, NEDI, INDI, and ICBI. Now we show the effect of the filter for a small portion of an image from the Morgfile 25 set. This is the ground truth image. This is a downscale version of the same image. Now the result from the ICBI algorithm, you can see it's not a bad result at all, but there is some blur at some parts of the image. Now the result from BNF, you can see that blur is very much reduced. It is a very sharp image. as you can see. BNF was able to improve the quality of images resulting from interpolation. In further work, we should consider other image sets and state-of-the-art base super resolution algorithms, and also a wider range of sharpening filters to be considered for the comparison. And that's it. Thank you very much. It was a pleasure to be with you. Bye-bye.
So thank you so much, Leonardo. So do we have any questions? I'm gonna have a look at YouTube or Wova. I think YouTube is more interesting for this kind of dynamics. So Leonardo, I was wondering here. So have you tried other distances, like instead of the Euclidean distance?
No,
To good, yeah.
no, João. Thank you very much for your question, João. Appreciate very much your interest on our work. Only the Euclidean distance. I am trying to learn a little bit about this type of color distance from the literature,
Yeah,
and
yeah, yeah.
we are interested on trying some other distances.
That could be maybe an extension of an interesting extension of your work, right? We have one question here from Leandro. He's asking, does the proposed technique work best with natural images or scenes made by man? I mean, it is context sensitive or not? No, you have any clue
Yeah.
or?
No, I think it's a very interesting question. Uh, I think it's not so much affected by the type of image, but since it's a sharpening filter, uh, we images with more a higher level of edges. Architectural images or images from buildings, it usually leads to a higher increase in the PSNR and structural similarity when
Yeah, I think
compared to natural images.
yeah, I think that the good point when you are not using machine learning is not context dependent, right? You can apply to any kind of image, right?
Of course, yes, sure.
And what about the efficiency, the computational load comparing to the others?
It's very cheap, very
Yeah, yeah.
efficient algorithm.
Mhm.
It's a very simple filter.
Right.
I would like to apply it to GPU as soon as possible. I am now I have a master student.
Mm-hmm.
The paper was written by me, coded by me, but now I have a master student. I expect to increase the range of applications,
Mm-hmm.
and the implementation should be improved. But it's very cheap, very efficient.
Yeah, it seems to be quite simple, and usually when the things are simple, they're much easier to do some things in parallel and to increment it. But that's a nice work. That's a nice work.
Thank you
Um,
very much.
so I think okay. So we don't have any more questions. I'd like to thank you, Leonardo, for your presentation. Right.
Thank you, João.
Uh, my pleasure. Thank you so much. Okay, let's move to the next presentation. Bye bye. Thank you. So we're gonna move to the next presentation. That is entitled "Image Denoising Using Attention Residual Convolutional Neural Networks." That is going to be presented by Rafael. Yes, please go ahead. Thank you.
Hello, my name is Rafael, and I will present you a summary of the work Image Denoising Using Attention Residual Convolution Neural Network. Noisy is usually defined as a random variation of brightness or color information, as shown by Figure 1, and it is often caused by the physical limitation of the image acquisition sensor or by unsuitable environmental conditions. These issues are often unavoidable in practical situations, which turn the noise in images a prevalent problem, that needs to be solved by appropriate denoising techniques. Denoising an image is a challenging task, mainly because the noise is related to its high frequency content, that is, the details. The goal, therefore, is to find a compromise between suppressing noise as much as possible and not losing too much details. The most commonly used technique for image denoising are the filter-based ones, such as the inverse, Richardson-Lucy, and Wiener filter. Besides filter-based techniques, there exists the non-learning dependent noise modeling approach, such as KSVG, BM3D, and Markov random fields. Such techniques are based on noisy prior modeling, and they figure some drawbacks such as the computational burden and the need to fine-tune parameters. Their effectiveness is highly dependent on the prior knowledge about the type of noise and its statistical properties. In an opposite direction, deep learning based techniques have become the most effective methods used in mainly many real world problems involving digital image processing, and likewise have been used as a natural replacement options for the non-learning dependent filter and prior knowledge-based denoising approaches. Such learning-based techniques tend to be less affected by the nonlinear characteristic of the noise generator mechanisms. State-of-the-art denoising CNN have been used in a training strategy called residual learning, where the network is trained to assimilate the noisy prior distribution. Another very interesting deep learning training strategy, not yet very explored for image denoising, is the attention learning. Such a mechanism is capable to make the deep neural network concentrate its learning effort in more informative components of the input data. The benefits of such a mechanism brings many advances in the area of natural language processing, recommendation system, among others. Here, we proposed a new learning-based non-blind denoising technique named Attention Residual Convolution Neural Network, and its extension to blind denoising named Flexible Attention Residual Convolution Neural Network. The proposed methods try to learn the underlying noise expectation using an attention residual mechanisms. Experiments on public datasets corrupted by different levels of Gaussian and Poisson noise support the effectiveness of the proposed approach against some state-of-the-art image denoising methods. Here are some results considering the proposed technique. Here, noise image cameraman. Here, noise image butterfly. Here, the second image is a restored image. PSNR is an image quality metric that the higher the value, the better the result. As we can see, we get good quantitative and qualitative results. Thanks.
So thank you, Rafael. Marcus is here to answer possible questions. Marcus is also one of the authors of the work. So don't we have any questions? Actually, since this is work by my students as well, I don't have any questions. Let's see if we got some in Wova. I'm gonna check here. It's a lot of tabs in my web browser, you know. Oh, I think we have no questions, so just wait a little bit. Yeah, we have no questions. So thank you, Marcus, Rafael,
Okay.
for
Thank you very much.
the work as well. Thank you so much.
Okay. Thank you.
So let's move to the next one. The next work is going to be presented by Danielle. That is called Sim Change Detection using Wood-Scale Cascade Residual Convolution Neural Networks. So thank you so much. Please go ahead.
Hi, my name is Daniel Felipe Silva Santos. In the next few minutes, I'll be presenting a brief overview about the work called Sim Change Detection using Multiscale Cascade Residual Convolutional Neural Networks, made by me and co-authors Rafael, Danilo, and João Paulo. The presentation is divided into four brief sections, named Proposed Approach, Results, Conclusions and Future Work, and References. In here, we propose a novel video segmentation method called Cascade Residual Convolutional Neural Network, MCR-CNN. That it follows same addressed methodology used by state-of-the-art techniques such as FG-SegNet_S, FG-SegNet_M, and FG-SegNet_V2. Which consists basically in video annotation, video images annotation, supervised training, and usage of the trained network to change detection. Here we have a picture illustrating the network architecture that consists in two networks, background convolutional neural network, BCNN, and segmentation convolutional neural network, SCNN. The BCNN is responsible to generate the so-called residual map that highlights high-frequency regions most related to the segmentation, the foreground ones. The residual map is pre-processed by a residual processing module responsible to apply a multi-scale processing strategy to it to generate a feature that is concatenated to the feature maps coming from the SCNN. The proposed MCR-CNN was evaluated on two data sets, being one of them a public one called Change Detection 2014, and the second one a private data set called Petrobras Routes. In the CD 2014, we achieved almost state-of-the-art results with F-measure precision recall above 0.95 and PwC around 0.1. With such results, the MCR-CNN overcomes CR-CNN, Cascade, GPS, IoTs5, PulseCS, and SubSense techniques. It was not capable to overcome results from the state-of-the-art techniques, but it was at least 8 times more compact in terms of the quantity of parameters. In the Petrobras routes, the MCR-CNN achieved state-of-the-art results overcoming FG-SegNet V2, FG-SegNet S, and CR-CNN techniques. We then conclude that Change Detection 2014 achieved almost state-of-the-art results with a very compact architecture, and also state-of-the-art results in case of Petrobras routes. And in the future, we pretend to investigate the problems regarding false negative detections. We'd like to acknowledgement CNPq, FAPESP, and Petrobras grants. Here we have some slides containing the references used in this presentation. Thanks for watching.
So thank you so much, Daniel, for your presentation.
Thank you.
Let's see. Well, we have okay. We got a question here to
Okay.
Ova. Let me see if you have some at YouTube. We don't have at YouTube yet. Oh, we do have one. Let's see. Okay, the first one is Danielle asked to Danielle, right?
Okay.
How difficult is, Danielle, to do hyperparameter fine tuning during training?
Okay. In such case, I have used already fine-tuned network called DCNN, used in restoration problems, and this architecture was evaluated by the authors of such of that work, and I inspired my design, my architecture design, almost in that almost all in that technique, in using the previous work as a reference base for that.
Right, and Falcão asked Danielle, what's the meaning? I mean, what's the purpose of using the IBN, right, and the IIN? Why do we use them?
Okay. Thanks for the question. The IBN means interleaved batch normalization, and IIN means interleaved instance normalization. Such approach tries to use batch normalization and instance normalization techniques, but at intervals of 3 by 3 layers. Such approach tries to alleviate the problem of using many operations during training or even during test of the network. So most for alleviate the overhead computation of the network.
Thank you, Danielle. Let me see if we have any more questions here. Right. Okay, I think we have no more questions for you today, Danielle. So once again, thank you so much for your presentation.
Thank you, João. Thank you all. Bye.
Bye-bye. And then I'm going to move to the last one. That's going to be presented by Italu's feature learning from image markers for object delineation. So please go ahead. Thank you.
Convolutional neural networks have revolutionized computer vision, with applications to various tasks such as object detection and identification. Since the first models, it called attention with competitive results. CNNs have become more complex, with a higher number of parameters. These models are considered black boxes, implying that one cannot explain their decisions. Thus, explainable artificial intelligence has appeared to address the problem and avoid wrong interpretation of the results. Besides choosing suitable architecture and training hyperparameters, the designer might also have to count on an expert of the application domain who must provide a dataset with sufficient number of correctly annotated samples for the model's training. Even though recent studies have focused on the first problem, none of them have considered exploiting both raised points. In this video, I'll talk about an interactive method to estimate the rates of convolutional neural networks without the need for backpropagation. Given the architecture of a CNN, this method called feature learning from image markers is able to estimate the weights of the features of the convolutional layers from markers in images. To evaluate the ability of these methods to produce good feature structures, we apply it to the problem of interactive object delineation. We compared feature structures learned with Flynn with feature structures from a lot more complex CNNs. Our proposal is only to evaluate the quality of the feature structures and not a new approach to the problem of interactive object delineation. Let X be a dataset of images. In this context, we don't want to classify images, but classify pixels. Therefore, each image pixel has a label. In an interactive object delineation problem, the label of a pixel says which object that object belongs to. We need to draw markers on these images in regions that we think are relevant to select the object or objects we want to segment. As the task is interactive, the user must place markers in all images. We can see each image as one dataset, so we can create a model specifically for each image. As Flynn can build a feature structure really fast, the user is able to build the model interactively. To do this, we draw markers in regions that we think are important for identifying the object. We take a patch around the marker's pixels. Those patches can overlap. We must do this for the other objects in an image or for the background. To choose which patches will be the kernels we use for convolution, we cluster these patches and take the centers of the clusters. We evaluated the following scenarios. We use the mean intersection over union as metric. Here, we can see the mean, max, median, mean, and the standard deviation of the mean intersection over union for each scenario. On average, GitLab's results
Yeah. Well, I think your presentation is just stopped, right?
Yeah, I think that's some problem because it shouldn't just stop.
Anna, are you there? Just wait for the please. All right, Anna, can you just try to that was it? That's all this in the presentation. All right. Maybe you sent something, the wrong presentation. Oh, that's okay. That's okay. Right. It seems that was the content of the file. Right. Let me see here. So, well, can you try? Let's Itulus, can you since I mean usually the presentations here are quite small, right? We don't have that much time to explain ourselves. So basically, you extract the patches that have been labeled by the user, right? And then you said that you're gonna use that patches as you're gonna cluster them, right? And then,
Yeah, I think that there was some problem with the upload of the video. It has more content after that. But yes, basically we have markers on the image, and we select patches around those pixels, and we'll use those patches to find a feature structure. Then we get the features that were extracted by those feature structures. We compute a gradient, and we use the watershed transformation to segment the object. Then we compare our feature structure learned with Flynn with other feature structures from the literature, such as the GitLab.
right.
We selected 2 blocks of the GitLab, the first block and the last block, to use it as feature structure. And this was it. And the results were comparing our feature structures with the feature structure from the literature.
And did you get like results that were better, close to them?
A lot better, actually, because we were not expecting that deep lab will perform so badly. But I think that as deep as you get, you are going to lose some useful information to select the object. So the grade of the output of the first block of the deep lab and the last block of the deep lab were really bad. So you actually couldn't use it to segment the object. So the result with all feature structures were a lot better.
That's nice. It's a nice idea. And simple as well, right? Your colleague here, Felipe asked if we could use our approach for super pixels. Can it be extended easily? Actually,
yeah, we could. Yeah, we could use the information of the super pixel, so we can have, instead of just using the information of the pixel that belongs to a marker, we could use the super pixel that has that pixel. So we have more information to learn the feature structures.
Right. That's going to be a nice extension, and it seems to be quite an easy extension, I guess. So let's see if do we have any more questions, guys? We don't have any questions at Wova. Yeah, well, I think we have no more questions. Unfortunately, we got a problem with your presentation, but I think you did a very nice presentation with all these objects moving around. It's going to be easier to understand.
I would like everyone to go to the program and watch the 50 minutes video. So there you can have an explanation of the method, how it works, the motivation, how we get to this method. So I really invite everyone to watch the video, and you can comment the video, so I'll try to respond if anyone has some questions.
That's nice. That's nice, Italo. So I think we have no more questions, right? Well, thank you so much, Italos, for your nice work. I'd like to thank everybody here that attended to this technical session. I'd like to also to thank Anna for helping us here with the technical stuff. And that is it. And I really hope you're gonna enjoy the whole conference. Right? Thank you so much, guys. Thank you all. And also thank you for all the speakers. Bye-bye.